Somewhere deep inside a laboratory at Aberdeen Proving Ground, Maryland, in January 2017, a group of materials engineers was quietly working on a routine experiment. They were trying to develop a new nanostructured aluminum alloy, one that would be stronger, lighter, harder. A better armor. Something that could protect soldiers and vehicles on the modern battlefield. The task was almost mundane by the standards of cutting-edge military research. Polish a sample, run a hardness test, record the data. Move on. But then something strange happened. The powder started disappearing. The engineers made another sample. Polished it again. And again it disappeared, dissolving almost silently in the water used during the polishing process. At first they thought it was a mistake. A contaminated batch perhaps. An instrument malfunction. But the data was undeniable. The water was doing something to this aluminum that water had never been reliably observed to do before at room temperature, without chemicals, without catalysts, without electricity. It was splitting into its components. And one of those components, hydrogen, was escaping in extraordinary quantities. The engineers had not discovered what they set out to find. They had discovered something far more consequential. What happened in that laboratory at Aberdeen Proving Ground is not a conspiracy theory. It is not internet pseudoscience. It is a documented, peer-reviewed, patent-protected scientific discovery made by the United States Army Research Laboratory, one of the most credible scientific institutions in the world. And yet, most people have never heard of it. Most people who fill up their gas tanks every week, who watch oil prices with anxiety, who worry about the future of energy on this planet, they have no idea this exists. This is the story of that discovery. Of the science behind it. Of the real human cost of the problem it was designed to solve. And of a question that, once asked, is impossible to ignore. If a powder that reacts with water to produce hydrogen fuel can be made for roughly $15 per kilogram, why is the world still running on oil? For most of human history, armies moved at the speed of their supply lines. Napoleon knew this. Grant knew this. Rommel knew this, and was stopped in the African desert not by British guns, but by the moment his tanks ran out of fuel. The relationship between armies and energy is as old as organized warfare itself, and in the 20th century, it became an absolute dependency. The modern military machine runs on petroleum. Tanks, helicopters, jets, generators, ships, trucks, all of it burns fuel. By 2008, the United States Department of Defense was supplying more than 68 million gallons of fuel every single month to support operations in Iraq and Afghanistan. Pentagon officials themselves reported that fuel demand for those conflicts was higher than for any war in the history of the United States. Every gallon of that fuel had to be bought, transported, stored, protected, and delivered, in a war zone, to the troops who needed it. That last part, the delivery, is where people started dying. Fuel convoys in Afghanistan and Iraq became some of the most dangerous assignments in the military. The convoys were large, predictable, slow-moving, and essential, which made them ideal targets. Insurgents knew that disrupting fuel supply lines would degrade combat effectiveness. They planned for it. They planted IEDs on the routes the convoys traveled. They staged ambushes. They hit the tanker trucks with rocket-propelled grenades. A 2009 report by the Army Environmental Policy Institute calculated that U.S. forces sustained 1 casualty for every 24 fuel resupply convoys in Afghanistan, and 1 casualty for every 39 convoys in Iraq. According to NATO and RAND Corporation estimates, approximately 3,000 American soldiers and contractors were killed or wounded protecting fuel supply lines between 2003 and 2007 alone. A separate analysis found that over a 9-year period of combined operations, more than half of all U.S. casualties, over 18,000 people, resulted from hostile attacks during land transport missions, the majority of which were fuel and water convoys. 80% of all cargo being transported in those war zones was fuel. These numbers carry a weight that is difficult to fully absorb. They mean that for every gallon of diesel that powered a generator, for every liter of jet fuel that put an aircraft in the air, there was a statistical probability that a human being would be wounded or killed to deliver it. Military commanders understood this. They called it the true cost of fuel. General James Mattis, during the drive to Baghdad in 2003, was reported to have said, "Unleash us from the tether of fuel." It was not a metaphor. It was a battlefield commander describing the most dangerous logistical vulnerability in the most powerful military in the world. The problem had a name. It had a body count. What it needed was a solution. The science of hydrogen as an energy carrier is not new. The element is the most abundant in the universe. When hydrogen combusts, its only byproduct is water vapor. When it powers an electrochemical fuel cell, a device that converts chemical energy directly into electricity. It does so quietly, efficiently, and with no exhaust. For decades, the promise of hydrogen has been held up as the clean energy future that perpetually seems to remain just around the corner. The practical problem has always been the same. Producing and storing hydrogen is expensive, dangerous, and logistically complex. The standard industrial method of producing hydrogen involves electrolysis, running electricity through water to split it into hydrogen and oxygen. But that requires electricity. Other methods involve natural gas, catalysts, or extreme temperatures. Storing hydrogen requires either cryogenic tanks that keep it in liquid form at -253 degrees Celsius, or high-pressure cylinders that carry significant explosion risk. None of these options are practical for a squad of soldiers on a long-range patrol in hostile territory. Nature, however, already knows a simpler path. Aluminum reacts with water in a process called hydrolysis. The chemistry is straightforward. Aluminum plus water produces aluminum hydroxide and hydrogen gas. The problem is that under normal circumstances, the aluminum immediately forms a thin layer of aluminum oxide on its surface, essentially rust, and that layer seals the reaction off. The hydrogen production stops almost before it begins. Scientists have known for decades that if they could prevent or disrupt the formation of that oxide layer, they would have access to a remarkably efficient and abundant source of on-demand hydrogen. The challenge was doing it without using toxic chemicals, extreme temperatures, or exotic catalysts, all of which would defeat the practical purpose. In January 2017, working in the Lightweight and Specialty Metals branch of the Army Research Laboratory's Weapons and Materials Research Directorate, a team of scientists discovered something that the scientific community had not previously achieved at scale: a way to permanently disrupt the oxide layer using the material's own structure. The key was scale. Specifically, nanoscale. The material they had synthesized, the one that kept disappearing in the polishing water, was an aluminum alloy designed at the level of individual atoms. By introducing trace amounts of other elements into the aluminum matrix at the nanoscale, the researchers created what is called a nanogalvanic structure. At this scale, the aluminum and the introduced elements form microscopic galvanic cells, essentially tiny electrochemical batteries, distributed throughout the material. When water comes into contact with the powder, these galvanic pairs create a localized electrochemical reaction that continuously disrupts the aluminum oxide layer before it can form and seal. The reaction does not stop. The hydrogen keeps coming. Dr. Anit Giri, a materials scientist who was one of the key researchers on the team, described it plainly. The powder causes the water to essentially break down. The extra elements in the alloy pull electrons from the water molecules, separating the hydrogen from the oxygen. And because this happens at the nanoscale, across millions of galvanic pairs simultaneously, the oxide barrier never gets a foothold. The results were extraordinary. The nanogalvanic aluminum powder produced 1,000 milliliters of hydrogen gas per gram of aluminum in under 1 minute at room temperature and atmospheric pressure. At 3 minutes, the reaction reached 100% of its theoretical hydrogen yield, 1,340 milliliters per gram. No heat required. No electricity. No chemicals. No catalyst. The reaction works with any liquid that contains water. Tap water, river water, seawater, coffee, urine. The byproducts, aluminum hydroxide, are stable and non-toxic. 1 kilogram of the powder can generate 4.4 kilowatt-hours of energy. To put that in perspective, that is enough to power 10 60-watt incandescent light bulbs for more than 7 hours. Or, using equivalent LED technology, for more than 50 hours. The powder can be pressed into tablets or sealed in vacuum pouches. Lightweight, stable, easily transported, with no inhalation risk, no pressure cylinder, no refrigeration required. The Army Research Laboratory filed for a patent in June 2018. The patent process opened a Federal Register notice inviting commercial partners to license the technology. In 2019, a hydrogen fuel company called H2 Power LLC became the first company to receive an exclusive license to explore automotive and transportation applications. The laboratory specifically noted that because both military and commercial markets could benefit, licensing the technology to industry would allow for mass production, which would drive down the cost per unit, enabling the Army to eventually purchase it back at commercial rates, significantly below what it would cost to manufacture internally. The cost of the raw material? Aluminum is the third most abundant element in the Earth's crust. The nanogalvanic powder can be manufactured using standard industrial milling equipment, at room temperature. Estimates for production at scale put the material cost in the range of $15 per kilogram, comparable to the cost of aluminum feedstock itself. This was the discovery. Now came the harder question. The military did not simply file a patent and walk away. The Army Research Laboratory, the Marines, MIT's Lincoln Laboratory, the Defense Innovation Unit, and a growing network of defense contractors and startups began translating the aluminum water discovery into deployable systems. At MIT, researchers developed what became known as the H2 the Hydrogen Tactical Refueling Point. It is a man-portable prototype that combines aluminum pellets with water to produce high-pressure hydrogen within 30 minutes, capable of refueling hydrogen fuel cell vehicles or unmanned aerial vehicles on-site. The system was demonstrated at Camp Lejeune, North Carolina, where Marine Corps commanders observed it refueling both a fuel cell-powered Polaris Ranger and a Polaris MRZR, the kind of light tactical vehicles used for reconnaissance and rapid movement in austere environments. The implications for drone warfare alone are significant. Hydrogen-powered unmanned aerial vehicles can travel 2 to 3 times farther and carry 2 to 3 times the payload of equivalent battery-powered platforms. In the Pacific Theater, where American strategic planning increasingly assumes operating across vast ocean distances against near-peer competitors, that range advantage could be decisive. Meanwhile, General Motors, working in collaboration with the Army's Tank Automotive Research, Development and Engineering Center, developed the ZH2, a hydrogen fuel cell tactical vehicle based on the Colorado truck platform. The ZH2 is nearly silent in operation. Its electric motor produces no smoke, no thermal signature, and almost no acoustic signature, 90% quieter than an equivalent diesel vehicle, according to Army measurements. It can travel 300 to 400 miles on a single fill of hydrogen. When stationary, it can export 25 kilowatts of continuous electrical power, enough to run a forward operating base, power communications equipment, or support a field hospital. And as a byproduct of its fuel cell operation, it produces up to 2 gallons of clean drinking water per hour. A tactical vehicle that generates its own fuel, its own electricity, and its own drinking water. From water. A Houston-based startup called NovaSpark Energy, founded largely by veterans, developed a hydrogen generation system called HITECH, hydrogen at the tactical edge of contested logistics, that uses wind and solar power to electrolyze water directly from the atmosphere, producing compressed hydrogen that can power drones, generate electricity, or be converted back into drinking water. The system runs on less than 30 decibels of noise, quieter than a dishwasher, and leaves almost no heat signature. It was demonstrated in April 2025 at Marine Corps Base Hawaii for commanders from U.S. Indo-Pacific Command. The Defense Innovation Unit funded NovaSpark's initial contract. The Army Contracting Command followed with additional authority. The Air Force's Innovation Arm, AFWERX, extended a contract as well. Multiple branches of the military across multiple commands and multiple years have quietly been investing in the same core insight, that water is the new fuel. What the science says, what the military has discovered through field testing, and what the economics increasingly confirm is that hydrogen, particularly hydrogen derived from aluminum-water reactions, is not a fantasy. It is a transition that is already underway in the most rigorous institutional environment in the world. The question is not whether it is technically possible. The question is what it means for everybody else. The global oil market is one of the most powerful economic and political forces in human history. Nations have gone to war over it. Governments have fallen because of it. For over a century, the entire architecture of industrial civilization, the roads, the supply chains, the geopolitics, has been built around the assumption that energy comes from burning things. That assumption is not merely an engineering choice. It is a financial infrastructure, a system of dependencies, a set of incentives so deeply embedded in the global economy that even the people who understand its costs most clearly have enormous difficulty changing it. The military, paradoxically, may be one of the institutions best positioned to accelerate the transition, not because it is ideologically committed to clean energy, but because it is pragmatically committed to operational effectiveness and the protection of the people it deploys. Every gallon of diesel that does not need to be trucked across hostile territory is a convoy that does not roll. Every convoy that does not roll is a set of soldiers who do not face an IED on a supply road in the dark. The nanogalvanic aluminum powder discovered at Aberdeen Proving Ground in 2017 is not a product you can buy at a hardware store. It is not commercially available at $15 a kilogram today. The manufacturing infrastructure does not yet exist at the scale required to produce it for the mass market. But the science is real. The patent is filed. The licenses have been granted. The field demonstrations have been conducted. The Army has shown, in conditions as demanding as any on Earth, that water can be made to yield usable energy on demand, without complexity, without danger, and without fossil fuels. There is something profound about the image of a soldier in the field, far from any supply line, dropping a small tablet into a container of water and watching a radio come back to life. It is not science fiction. Dr. Chris Darling, a materials scientist at the Army Research Laboratory, described exactly that scenario publicly: a squad on a long-range patrol with dead batteries, powering their radio with nothing more than the aluminum tablet and whatever water they could find. Urine, he noted, works just as well as distilled water. In some tests, it actually produces hydrogen at nearly twice the rate. The energy future is not going to arrive all at once. It will not arrive cleanly or without disruption. There will be resistance, economic, political, institutional, from those whose interests depend on the continuation of the old system. That is not a conspiracy. It is simply how large systems behave when they are asked to change. But somewhere in the gap between what is technically possible and what is commercially available, between what the military has already demonstrated and what the civilian world still believes to be science fiction, there is a story worth telling. There is a discovery worth knowing. There is a question worth asking. In January 2017, at a laboratory in Maryland, a piece of aluminum disappeared into a puddle of water and produced hydrogen. Nobody planned for it to happen. Nobody had a theory predicting exactly that outcome. It happened because science, at its best, is willing to be surprised. The world has enough aluminum to cover every energy need on the planet many times over. It has enough water. It has the chemistry, the engineering, and now the proof of concept. What remains is the will to make the transition, and the knowledge that it is already further along than most people realize. The Army's forgotten hack is not forgotten by the Army. It is under development. It is being tested. It is being licensed. And the water we drink, the water that falls from the sky, the water that covers 70% of the surface of this planet, all of it is quietly waiting to become something more.